Alright, this video is on limits and continuity. I've done a little work ahead of time here where I've written up some limit principles that we'll be using in the section. If you're in my course, you will find this as a handout along with the video. But just to go over this together quickly before we do some examples. So the first limit principle says if the limit as x approaches a of f of x is equal to L, so is equal to some value L, and the limit as x approaches that same value a of a different function g of x is equal to m, then we have the following properties. So the first one says you're taking the limit as x approaches a of a constant, so c is a constant here, then it's just equal to that value. So, you know, if this is the limit as x approaches a of 7, then it would be equal to 7. If it was the limit as x approaches a of 5, then it would just be equal to 5. Because if it's a constant, that's like the function y equals a constant. So if y equals a constant, then it's the same value everywhere. The second property we have here is that for any positive integer n, the limit as x approaches a of f of x raised to the n power, so the entire function raised to the n power, is equal to the limit of the function raised to the n power, which we know the limit as x approaches a of f of x is equal to L, so we're just replacing that with L here. So it's really equal to the limit of the inside raised to the n power is what it's really showing. The limit as x approaches a of two functions either being added or subtracted, you can take the limit of each function individually and then just add their limits. So this is why the limit as x approaches a of f of x plus or minus the limit as x approaches a of g of x is just equal to this limit, which was L, plus or minus this limit, which was m. Similar but different, if you have multiplication of two functions and you're taking the limit, that's equal to the limit as x approaches a of the first function times the limit as x approaches a of the second function. So that's really going to take this limit, which we know was L from earlier, times this limit, which was m from earlier, so it's just going to be Lm. So you multiply them together. If you have a product inside of the limit, you can take the limits of each of those individually and then take the product of that. Similar rule for division. The limit as x approaches a of a function divided by a function, right, is equal to the limit of the numerator function over the limit over the function in the denominator. So in this case, the limit as x approaches a for f of x is L, the limit as x approaches a for g of x is m. So we get L over m, and then we just caution that the limit here for as x approaches a for g of x can't equal 0, otherwise this would be undefined. And then the last couple rules we have the limit as x approaches a of a constant times a function. Well, what you really can do is take that constant to the front and just take the limit as x approaches a of the function. It really is built off of the rules that we talked about earlier. The limit of the constant is just the constant, so that can stay, times the limit of the f of x function. So it's constant times this limit here, right, this piece is L. And then the last one is the limit as x approaches a of x. So if this is just you know, the variable x, the function, you know, is f of x equals x or y equals x, then as x approaches a, you can just say it's going to go to a. In other words, you know, it's the identity function, right? Y equals x. You're subbing in a for x, so equals a. So we'll use these properties to help us throughout the section, but just making sure that we have them before we go forward. We're going to be very specific with the first example. Afterwards, we'll kind of shortcut them a little bit. So if I said, for example, find the limit for, and we'll say we've got the limit as x approaches 4 of x squared minus 3x plus 7. So if you watched my last video, I did refer to if you have a polynomial, you can just sub the value in. Here what we're going to do is we're going to use the rules that we just talked about, these limit principles, just to show why that's true. All right, so we'll start with just saying, okay, if I have addition or subtraction of a polynomial in here, our rule that we had for number 3, so that we could take, you know, the limit of each of the terms individually. So I could take this as the limit as x approaches 4 for x squared minus the limit as x approaches 4 for 3x plus the limit as x approaches 4 of 7. And then after that, we'll apply the other rules, again, just to show you how it works. So here, this is the limit as x approaches 4 of some function being raised to a power. Remember, we said, based on rule number 2, that I could take the limit as x approaches 4 of just x, and then that's raised to the power. Minus here, limit as x approaches 4 of 3 times a function. Remember, the constant can be brought to the front. That's from rule 6. And this is the limit as x approaches 4 of x. Right, so it's 3 times that. And then plus the limit as x approaches 4 of 7. 7 is a constant. This was rule number 1 we talked about. It's just equal to the constant. It's equal to 7. In other words, as x approaches 4, y equals 7 is always y equals 7. So it's just going to be 7 for that limit. And then evaluating these individually, we have the limit as x approaches 4 of x squared. Well, the limit as x approaches 4 of x, remember from our last rule we said the limit as x approaches a is just a. So limit as x approaches 4, well, this is just like y equals x, so this will be just subbing in 4. So this will be 4 squared. Minus here we have 3 times. The limit as x approaches 4 of x. Remember, you just sub in that value for x, so this will be 3 times 4. And then we have plus 7. And we simplify this just like you would for order of operations. So this equals, we have 4 squared is 16, minus 3 times 4 is 12, plus 7. 16 minus 12 is 4, plus 7. This equals 11. So, I mean, that's using the properties that we just talked about, right? Those limit principles. You don't necessarily have to use them. You can kind of see this, right? Because this is a polynomial, and it's really because this is continuous, you can see that if I just subbed 4 in right away, I would have been doing the same thing, right? subbing in 4 for x, we would have 4 squared gives us the 16, minus 3 times 4 gave us the 12, and then plus 7 gives the 7, so it equals 11. So, you know, I wouldn't expect you to show all these steps. I just want to show you why substituting in the x equals 4 right away works. Now, you can only do this in the case where your function turns out to be having the x value in its domain, and we'll talk about that in a minute. For a polynomial, since their their domain is from negative infinity to infinity, you can always substitute in. But we'll talk about that a little bit further. So we have a theorem here for any rational function. All right, so we'll write this out and then we'll show an example. So this theorem says for any rational function, the limit as x approaches a of f of x, right? So f of x is a rational function, equals f of a. In other words, you can substitute a right in there, but this is important. If a is in the domain of f of x. Right? In other words, the function has to exist there. If it doesn't, then you can't just substitute right in, which kind of makes sense, right? When we say rational function, make sure you understand rational function means a function that's expressed as a fraction using a polynomial numerator and polynomial denominator. So you can substitute a right in as long as a is in the domain. If a isn't in the domain, you can't substitute it right in and evaluate. So let's take a look. If I said, for this example here, find the limit as x approaches 3 of x squared minus 9 over x minus 3. So first off, you should notice what the domain is, right? In this case, for our domain, we're looking for x values that cause problem points. In other words, we can make this undefined. Well, if we have x minus 3 in the denominator, when x equals 3, right, that's a problem point. It would cause it to become undefined. So we know x doesn't equal 3, right, because it's not in the domain of this function. So I can't just sub 3 right in here right away. You can kind of notice it, right? If I did 3 squared, it'd be 9 minus 9. That's a zero numerator. That's okay. But 3 minus 3 in the denominator would make it undefined. And so you couldn't just substitute 3 in and evaluate the limit. So what we're going to do is we're going to talk about factoring this, right? So simplifying this, we're going to simplify this by factoring. So this will be the limit as x approaches 3. Make sure you always write the limit notation first. So limit as x approaches 3. Now x squared minus 9, how does that factor? Well, it factors to x plus 3 times x minus 3 is the difference of perfect squares all over x minus 3. Now if you remember from my earlier videos, you're allowed to cancel these factors because we know x doesn't equal 3. So we know that these are not going to be 0. So we're allowed to cancel these because x doesn't equal 3. And then I'm left with just the limit as x approaches 3 of, well, this cancels just of x plus 3, right? And now that I've canceled those, I'm left with the limit as x approaches 3 of x plus 3. This equals just substituting in 3. So now I can substitute 3 in because it's in the domain of this function. So 3 plus 3, which equals 6. So the limit as x approaches 3 of x squared minus 9 over x minus 3 is going to be equal to 6. And if you remember earlier in the course, if you watched my earlier videos, these cancel here, right? Because we know x doesn't equal 3, so it's not in the domain. So we're allowed to cancel those because we know it's not 0 over 0. But also, this gave us some properties of the graphs. Remember, we said there was a hole at this value when x equals 3. So something to keep in mind, we'll talk about that in a little bit. What if I asked you this? Maybe I'll do it right next to it. So, same function, but if I said find the limit as x approaches 4 of x squared minus 9 over x minus 3. So the limit as x approaches 4 of x squared minus 9 over x minus 3. The thing you should notice here is that the domain is just x doesn't equal 3, right? 3 is the problem point. All the other x values are in the domain. So since 4 is in my domain, I am allowed to substitute it in. It's really what this theorem says. For any rational function, right, the limit as you approach the x value can just be substituted right in to evaluate the limit if a is in the domain of f of x. So if that number, in this case 4, is in the domain. So since we know it's in the domain, then you can say, let's take the limit as x approaches 4 of x squared minus 9 over x minus 3. You don't even have to factor in cancel. You really can just substitute it in immediately. So we would have 4 squared minus 9 over 4 minus 3. 4 squared is 16 minus 9 over 4 minus 3 is 1. So this would just equal 7, right? 7 over 1, which just gives you 7. So this limit is equal to 7. The function also exists there, and you can kind of see that because you substituted it right in. We'll talk a little bit more about that in a second. So from here, right, you got to make sure you understand why you do what in each case. In this case, 3 wasn't in our domain. We couldn't substitute it in immediately. In this case, 4 was in our domain, so we could substitute it in immediately. Let's take a look at this here. If I said, for example, I had the limit as h approaches 0, 2x squared plus 2xh plus h squared. So the first thing I want to point out is that you have two variables in here. Make sure you're looking at the correct one. We were looking at the limit as h approaches 0. In addition to that, all we want to do is say, okay, is h in this domain? Well, it is, because there are no issues in terms of h being equal to 0 being undefined. So our value of 0 is in this domain, so we can just substitute it in right away. So you really would just say, okay, I'm going to sub 0 in everywhere I see an h. The x's are going to stay x's, that's okay. It just stays as a function. So you have 2x squared plus 2x times h, which is 0, plus h squared, which is 0 squared. And then we simplify this. Well, this is 2x squared, stays 2x squared, plus 2x times 0 is just 0, plus 0 squared is plus 0, so this equals just 2x squared. So in this case, this limit ends up being being a function, and that's okay. You can have an expression like this. It doesn't have to always be a numerical value. In this case, since we had two variables, you're going to have variables left in there since we're only taking the limit as you approach for h going to 0, right? We're not talking about x. So those are just some examples using the limit. The limit tells us about continuity, and I'll give you an informal definition and I'll give you the formal definition afterwards. The informal definition is really just to have an understanding of what continuity means. The formal definition will actually be the way you show something is continuous. So this part of the section is on continuity, and here's the informal definition. And we'll talk about it in terms of a graph you might see. So a function is continuous over an interval if you can draw it without taking your pencil off the paper. Very informal way of describing this, right? So I'm saying, all right, a function is continuous over an interval if you can draw it without taking your pencil off the paper. What this is really trying to say is that there's no breaks, right? So there's no jumps, no breaks, and no holes in the graph. Right, so that's really what this is getting at. So let me give you a few examples just so you can kind of ID what we're talking about. So, for example here, I'm just going to draw a few small sketches. So here's an x-axis and a y-axis, and you know, if I drew this function here, so this is at 1, maybe an open circle, and it looks like this, right? That is not continuous. And it's not continuous because there's a hole here, right? So there's a spot in our graph where if I was following from left to right, that I just can't keep drawing it, right? I have to put a hole there and then continue on. You might also see something like this, another x and y axis. Suppose you had something that had asymptotes. So, you know, it looked like that. Well, again, we have to draw this. We take our pencil off the paper here, draw this first part, and then draw the second part. So this one is also not continuous. And I'm going to use CTS for continuous just as a shorthand, so we don't have to spell it out every time. And if I was to draw this one here, if I call this x and this y, and suppose I had, I'll call this -1. Suppose I had something like this, where it looked like that. That one, is that continuous? The answer is yes, right? Because there's no jump, break, or hole. It has a weird, you know, two pieces. It's kind of piecewise, but it does continue on. There's no jump, break, or hole at that point. So this one is continuous, and that's okay. Some of them will be continuous, some of them won't. Now, this is just a way of identifying visually. The formal definition that we use in calculus is a little more based on, you know, performing some algebra and making sure that it actually meets some criteria. So we're going to take a look at that now. So this is your formal definition. This is what I actually expect you to use if I was to ask you if something is continuous. So for this definition, a function is continuous at x equals a. So we're talking about continuity at a point, right? So at a specific point when x equals a being some real number value, if, and here's the properties, 1, f of a exists. In other words, if you have the function, you can substitute the value for a in and you get a y value out, right? That's when f of a exists. So first part is if f of a exists, you're on the right track. The second criteria you need to meet is that the limit as x approaches a of f of x exists. Now remember, this is different than the first criteria, right? The first criteria was just saying the function exists at the value. The limit as x approaches a of f of x existing, all that tells you is you get really close to the x value of a, right, from both sides, that the function approaches the same y value on both sides. So as you get really close. Doesn't matter what happens at the value, it just happens when you get really close to it. And you need all three of these criteria. So the function has to exist at the point, the limit has to exist as you approach that value for a, and the third criteria is that these have to be equal to one another. So the limit as x approaches a of f of x equals f of a. So you find if the function exists at that value, you find the limit as you approach that value, and then you determine are those the same. If they are the same, then it's continuous, right? That's what this last step tells us. If they aren't the same, like if limit as x approaches a of f of x does not equal f of a, then it's not continuous. And there's some sort of jump, break, or hole there. So really what we're doing is we're inspecting to see, if, where the function value is, if there is a hole or a break or a jump compared to where the limit is. So we'll do a couple of these. And these are the steps I would expect to see if I ask you if something is continuous. So determine if f of x equals 3x plus 7 is continuous. And I'll use CTS to abbreviate continuous at x equals 2. So first off, make sure you understand what a is. A is the x value we're talking about, right? So they're telling you a equals 2. So if I'm following this, right, if I'm following this process, the first thing I want to do is, right, for my solution here, is check, okay, does f of a exist? Right, so you're checking this for the criteria that we need above. That's how I'm picking out what to do first. So I'm checking to see, can I evaluate f of 2? Well, if I was looking at f of 2, because remember that's f of a, I'm going to have 3 times 2 plus 7. 3 times 2 is 6. 6 plus 7, that's 13. So yes, f of 2 exists, right? It's equal to 13. Now it doesn't mean it's continuous, it just means that the function exists at that point. The second thing you want to look at, right, is the limit, right? So the limit as x approaches a. So this will be the limit as x approaches, in this case a is 2, right, of f of x. Does this exist? Well, that means that when we do this, right, we're going to take the limit as x approaches 2 of f of x is the 3x plus 7. And from earlier, if you remember, right, as long as we have something that, 3x plus 7, 2 is in the domain for 3x plus 7, we can substitute 2 right in. And since the domain of 3x plus 7 is all real numbers, I could substitute into that right away. So I have 3 times 2 plus 7, which is 6 plus 7, which equals 13. So the limit does exist. Now, I know this feels a lot like what you did above, but you do have to show that this is the limit here, because it won't always be the same. In this case, it happens to be, but it won't always be the same. So you do have to show this limit exists, and you do have to write it in the correct notation. So the first part existed, right? The second part existed, right? So the function at that value existed. The limit as you approach that value of the function exists. And then the third criteria, what you're really checking is, does the limit as x approaches 2 of our function f of x equal f of 2, right? That's what step 3 really told us from above. That was what we have to look for. Well, in this case, let's take a look. We've got f of a is 13, right? F of 2, in other words, is 13. And this limit as x approaches 2 of f of x, well, that's 13, so 13 equals 13. It checks out, right? So this limit here is 13. F of 2 is 13, right? That's, this first part here is from step 2. This is from step 3. 13 equals 13. It checks out. Make sure you make some sort of statement here. I'll say, just to make sure we know it, these 3 dots mean therefore. So therefore, f of x is continuous, right? That's what it's asking us about. Is it continuous? So f of x is continuous at x equals 2. And that's really the answer, right? Everything else above it is showing why that's the answer. That's the actual answer. Keeping in mind that, just because it's continuous at x equals 2 doesn't mean it's continuous everywhere. So you have to be specific saying it's continuous at x equals 2. There could be functions that are continuous at some values and not others. So you have to really look at what you're trying to show. So in this case, we're showing it's continuous at x equals 2. So this one was more straightforward because our function was a polynomial. It's a little easier to work with. Let's take a look at a couple others. So if I was to look at this function here, is f of x equal to, and it's going to be a piecewise function, 1/2 x plus 1 for x less than 2, and negative x plus 5 for x greater than or equal to 2. We want to know, is this continuous at x equals 2, right? So that's the question. So we have to follow the process for, what makes a function continuous, what defines it as continuous. Remember, in this case, our a, right, is equal to 2. So what we talked about before, step 1, right? We want to know, does f of a exist? In other words, does f of 2 exist? Well, we substitute it in and see if we can get a value out. So f of 2, make sure you understand where this is coming from. In a piecewise function, you want to do it in the appropriate part of the domain. You don't do it to both, right? We're subbing in 2, and we're trying to find the y value that goes with it. That's what f of 2 means. So you'll be using the second part because that has the equal to condition on the 2, right? 2 is contained in this interval, not this one. So f of 2 is equal to, we're using the negative x plus 5. So it's negative x is 2 plus 5. And negative 2 plus 5, well, that equals 3. So f of 2 equals 3. The main thing here, though, is that it exists, right? So that's the first thing that you're looking for. The second thing you're looking for is you want to know if the limit as x approaches a, so in this case, the limit as x approaches 2 of f of x exists. Now, when you're finding this limit, right, in this case, remember, we don't care what happens exactly at 2. We care what happens as you approach 2. So since this is defined differently from the left and right side, you do have to do 2 limits. So a limit from the left and a limit from the right because it splits at this value of 2. In the previous one for the polynomial, it was defined the same on both sides because it was always defined as that single function. So you didn't have to worry about it. But here you do. So we actually need, right, to see if this exists, we need the limit as x approaches 2 from the negative side, meaning from the left side of f of x, and you want the limit as x approaches 2 from the right side, so the positive side, that little positive side means the right side or the positive side of f of x. And you want to find these individually, and if they come out to the same thing, then the limit exists. If they come out to different answers, then the limit does not exist. So for the first one, the limit as x approaches 2 from the negative side, well, which function am I going to use? I'm going to use the one that is less than 2, right? From the negative side or the left of 2, or the value is x less than 2. So I'm using the 1/2 x plus 1, and I'm evaluating this limit. Well, is 2 in the domain of this function? Yes, it is. So I can really just write this as the limit as, actually I don't even have to write the limit. I can just write this as equal to, I can substitute it in right away, right? So it's equal to 1/2 times 2 plus 1. Don't throw that negative in here. It's not the sign of the number, it's the side of the number you're on, right? So we're on the left side, what that negative sign tells us. And then we evaluate it. 1/2 times 2, well, it's just 1, and 1 plus 1 equals 2. So the limit from the left side, right, is equal to 2. And now we'll do the same thing here for the right side. On the right side, we say, you know, this is going to be the limit as x approaches 2 from the positive side, or the right side. Remember that plus means the right side. And for the right side, well, we're using this function because this is where the x's are greater than 2. So this would be of negative x plus 5. And since we know that 2 is in the domain of this, we can substitute it in right away. So this is really negative x, so it's negative 2 plus 5. And we know that equals 3. So does this limit exist? That's what this is really asking us to find. And the answer is, you know, just for this limit to exist, coming from the left side has to be equal to coming to the right from the right side. And since they're not, then the limit does not exist. So just as a quick therefore, a summary here. All right, so therefore, the limit as x approaches 2 of f of x, and we'll use dne for does not exist. And the reason it doesn't exist is since the limit as x approaches 2 from the left side of f of x does not equal the limit as x approaches 2 from the right side of f of x. And I know it might feel like you're done, but we didn't actually answer the question yet. What was the question? The question was, is this continuous? So remember, to be continuous, the function value had to exist, the function at the value had to exist, the limit as you approach the value of the function has to exist, and then if those are equal, then it is continuous. But if this doesn't exist in step 2, right, which we just found, then you don't have a chance of being continuous. It has to meet all 3 criteria. So because of this, we can say, therefore, f of x is not continuous, right? CTS is for continuous at x equals 2. That's actually the answer. Don't forget to answer the question we're asking, right? So f(x) is not continuous at x equals 2. It doesn't mean it's not continuous at other values. If actually I picked any other value other than 2, this function would be continuous there, because the part where it's broken up is at 2. But you would have to show it as well. You can't just say it. You'd have to show why in terms of the function existing at the point, the limit existing as you approach the value, that x value, and then, you know, those being equal to each other. But in this case, we can't even find the limit because it doesn't exist. So then the function is not continuous at that value. We'll look at one more. So this last one here, we'll say this example is going to be, I'll call the function g of x, but it doesn't change anything. So is g of x equal to, piecewise again, the first piece will be x squared minus 16 over x minus 4. And this condition is for when x does not equal 4. And we'll say it's equal to 7 when x equals 4. And we want to know, is this continuous at x equals 4? Now you may want to pause it and try it out on your own. And, you know, make sure you're following our criteria. For the first part of our criteria, remember we want to make sure that g of a, in this case g of 4, exists, right? So the first thing is that you want to make sure the function exists at the point. Well, g of 4, what's that? Well, looking up here, when x equals 4, g of 4 is 7. So it's just 7. Right, so it exists there. It's actually telling you the point 4 comma 7 is on your graph. But don't substitute it into both, right? You're not doing that. It's saying, does g of 4 exist? Well, that means sub in 4 into the function where it belongs and then evaluate that. You can't use the top part of this piecewise function because that's for when x doesn't equal 4. All right, so we know the function exists at the point. So we're in business, it might work. Step 2, we want to make sure the limit as x approaches a, which in this case is 4, of g of x exists. Now when I look for the limit, remember how you find the limit. You're looking to the left, from the left and the right of that x value. It doesn't matter what happens at the x value, right? We don't care about that. What happens as you approach the x value. So when I look at this, right, my function from the left and the right is this top function here, right? This is only for when x doesn't equal 4. So from the left of 4, you're using this. From the right of 4, you're using this. So you really only have to find one limit because it's the same function for both, right? So I can say that I want the limit as x approaches 4 of, we're just using the x squared minus 16 over x minus 4. You don't use the 7 in this because that's only when x equals 4, and limits don't have anything to do with that. You could talk about this from the left and the right, but since it's the same function from the left and the right, it doesn't make sense to write it twice. Here we only have to do it once. In the previous problem, just going back a second so you see it, we had to do it twice because our value of a was at 2, and on the left side of 2, it was different than the right side of 2. So that's why I used the left-hand limit and the right-hand limit to make sure that from both sides it was going to the same thing. In this case, though, it's the same function on the left side and the right side of 4, right? Because that's what this really tells us, just for when x doesn't equal 4. So we can just use it right away. And then if you want to evaluate this limit, the first thing you should ask yourself is 4 in the domain of this? Well, the domain of this function is for when x doesn't equal 4. They told us up here. You can also recognize it here, right? It would make it undefined. So you don't want to just sub 4 in right away. You can't. So remember, if it's not in the domain, right, you can't sub it in. So what we're going to do is we're going to factor, right? So make sure you keep writing limit here, right? So it's the limit as x approaches 4. You need that. It's telling us what to do. And we're going to factor the x squared minus 16 would be, you know, difference of perfect squares, x plus 4 times x minus 4. And then this is still over x minus 4. So knowing how to factor is important here. Sometimes you'll forget how to factor. I mean, this is difference of squares. You might also have trinomials here, so make sure you pay attention to that and go over those factoring rules if you don't remember. And then remember, what I want to do is I want to try to cancel. In this case, if you can have the same factor in the numerator and denominator, they cancel out. The x minus 4 is canceled. The reason we're allowed to cancel these, remember, is that we know x doesn't equal 4 here, right? That's because it's not in our domain. So this is not 0 over 0. So I'm allowed to cancel those. And I'm left with this limit that ends up being the limit as x approaches 4 of just x plus 4. Now, to evaluate this limit, 4 is in the domain of this, so I can evaluate it by just substituting in. So we have 4 plus 4, and this equals 8. So, yeah, the limit exists, right? We found that. So the function exists, right? G of 4, right? So the function exists at the point. We got g of 4 equals 7. The limit exists at the point, which ends up being 8, or the limit exists, I should say, as you approach the point, right? So that ends up equaling 8. And then the last part of our definition says, okay, to be continuous, the function value, right? We want to make sure the limit as x approaches 4 of g of x is equal to the function value. So that's what I'm asking myself. Are these equivalent? Is the limit, what you got from step 2, equal to what you got from step 1? Well, the limit as x approaches 4 of g of x, that's what we just found in step 2, that's 8. Does that equal g of 4? Well, g of 4 was 7, so 8 doesn't equal 7. So then, no, right? So that part doesn't work, and what's that tell us? Make sure you write a statement. So then, therefore, g of x is not continuous at, and we're talking about continuity at a point, so at x equals 4. So, I mean, you can kind of see where this came from, right? We asked if it was continuous at x equals 4. Now, if it was at a different x value, right, this function would be continuous at those points. You would have to do the work to show it, but it wouldn't have the issue of these not coming out equal. The other part I want to mention here is that what you really did when you did this is, if you remember, we talked about it earlier, when you cancel these factors, it's telling you there's a hole, right, when x equals 4 in our graph. So the hole is at x equals 4, and then the value of where the hole occurs, the y value, would be 8. That's what happens when you sub into here. So there's really there's a hole, just as an aside, there's a hole at the point 4 comma 8. Now what we're really checking, what we're checking down here, is that does the function value, right, this g of 4, does it fill in the hole? Because if g of 4 was equal to 8, that would make this continuous. So sometimes you might be asked a question where you kind of have to think a little bit, saying, okay, what would the y value have to be here, right? What would this number have to be here in order to make this continuous? Well, g of 4 would have to be 8, and if g of 4 was 8, then that would make it continuous, because then the function value would equal the limit value at the point. So just something to keep in mind, but in this case, right, it's not continuous because the limit as you approached 4 was not equal to the function value at 4, so you know that g of x is not continuous there. So anytime you're showing continuity, make sure you're showing the 3 steps, and then making sure you're giving me the correct reason why it is continuous or not continuous in the end. So hopefully this helps.